What are efficient cooling system design principles? Have you ever wondered how engineers keep machines and electronics from overheating? Efficient cooling system design is key to managing heat effectively. Let's break down the principles that make these systems work well. First, understanding heat transfer is essential. There are three main ways heat moves: conduction, convection, and radiation. Conduction transfers heat through solid materials, while convection involves fluids like air or water carrying heat away. Radiation is when heat travels through electromagnetic waves. A good design maximizes conduction and convection, often using materials that conduct heat well and improving fluid flow to enhance cooling. Next, material selection plays a big role. Choosing materials with high thermal conductivity for parts like heat sinks helps dissipate heat better. It's also important to pick materials that are durable and resistant to corrosion. This ensures that the cooling system lasts longer and performs reliably. Fluid flow design is another critical factor. In liquid cooling systems, the shape and layout of coolant channels can greatly affect how well the system works. By designing channels to maximize contact with the heat source and keeping coolant flow uniform, engineers can reduce hot spots and pressure losses. The shapes of these channels, whether rectangular or circular, are optimized to balance heat transfer and minimize energy loss. The layout of the entire cooling system also matters. The arrangement of components like pumps, radiators, and fans should promote smooth fluid flow and effective heat exchange. Engineers often use computational fluid dynamics to simulate how fluids move and heat transfers, helping them create the most efficient designs. Applying thermodynamic principles ensures that the system maintains the right temperature by balancing heat input and removal. Fluid dynamics help control how fast the coolant moves, improving heat transfer while keeping energy use low. Targeted cooling is another smart strategy. By focusing on areas that generate the most heat, such as engine parts or electronic components, systems can operate more efficiently. This approach directs resources where they are needed most. Energy efficiency is a must. Cooling systems should perform well without consuming too much power. Selecting fans and pumps that provide the necessary flow rates at the lowest energy cost is key. Reducing pressure drops in the system also helps lower energy needs. Finally, simulation and testing are vital for validating designs. Engineers use simulations and physical tests to ensure the system meets cooling needs under different conditions. This helps fine-tune fan and radiator choices, coolant flow rates, and channel designs for optimal performance. Practical examples of these principles in action include automotive engine cooling systems. Here, optimizing radiator size and coolant flow helps maintain engine temperature and prevent overheating. In electronics, cold plates with well-designed coolant channels efficiently remove heat from high-power components. Efficient cooling system design combines heat transfer knowledge, material science, fluid mechanics, and thoughtful component arrangement. This approach is essential in various fields, ensuring reliable thermal management while keeping energy use to a minimum.